So let me try to tell you a bit about categorification. So just to begin with, if you haven't seen this before, well, what is categorification? If you look that up on Wikipedia, there is a nice Wikipedia page, and basically what you will find there is this. So categorification is the process of replacing set theoretic notions and theorems by category theoretic analogs. So basically, you replace sets by categories, functions by functors, and equations by natural transformations or isomorphisms. And then you get some perhaps further structure and properties. And just to get started, to give you an idea what that, basically, easiest example would be, well, take the category of finite sets. That's a nice category. And that is a categorification of the natural numbers. So why is that? Well, the idea is, if you look at isomorphism classes of objects, well, basically then you get back the natural numbers. Just the number of elements in your finite set will give you a natural number, and this up to isomorphism describes your finite set. And, well, this is basically what one means by decategorifying a category. So you just get back a set, the set of isomorphism classes. But, okay, there is a bit more structure you can find in the category finite sets, well, addition and multiplication, which is disjoint union and Cartesian product on the categorical level. Well, this is perhaps the easiest example of a categorification you can think of. It's not very useful. I mean, it's just another way of thinking about finite sets. So one important remark is that categorification is not a well-defined or rigorously defined process. It's not that you give me a mathematical structure and then I return to you a categorification of it. It's a bit similar to quantization. You have to, come up in every single example, you have to come up with an idea of how to produce an interesting categorification, and usually you might end up with inequivalent results. Just a very simple example. In the previous example, instead of looking at finite sets, you could also take the category finite dimensional vector spaces. That's basically, again, parameterized by natural numbers. Just take the dimension of your vector space. But of course, the morphisms now look different in this category, so it's not the same categorification as finite sets. Again, this is just in order to illustrate this. Some further examples. So one example that will come up again later is that basically monoidal categories should be thought of as a categorification of algebras or rings, if you like. So if you add some more adjectives, you can have if you just have a monoidal category, that would probably correspond to just a ring. And if you add maybe a C-linear categories or C-star categories, you can think of more sophisticated sorts of algebras, categorified algebras. Well, then there are two more examples which I'll not go into. I just want to mention Cohomology homology because Cohomology homology is really an interesting example of a categorification which tells you more than what you knew before. So you can get back the Jones polynomial from Cohomology homology, but Cohomology homology is stronger. So there are examples where categorification really gives you new insight into mathematics. Okay, so that's basically a short introduction to categorification. We will only need a tiny bit of higher categories and this machinery, and what we will need is the notion of a categorical group or a two-group, and I want to briefly explain to you what that is. So basically, you can ask what happens if I want to categorify groups, well, this is quite well understood. And basically a two-group, well, it's a category which should, the category should be the underlying set of your group, like the underlying set of your group, and then you have a multiplication and an inverse and unit element, and these are now given by certain functors, and then you have some axioms which should be satisfied. And you can write it all out, and it's not too hard to do that, and what you find is that, so one way to phrase two groups is to say that they are group objects in the category of categories. That's basically what I've written up there. But you can rephrase this in various ways, and I've just written that down. So the only one which will be important to us is the last one. So two groups can be explained or can be encoded in terms of crossed modules of groups. And so that's what we will focus on, crossed modules. And let me just tell you what a crossed module is. An object is invertible with respect to tensor product. So, right. Okay, so crossed modules. If you haven't seen this before, well, this is the definition. Well, I mean, the point about crossed modules, I think, or the way I think about them is that basically they encode three-step extensions of groups. So the way to think about cross modules, basically you can forget about the definition. The important thing is every such cross module gives you a three-step extension of groups where, okay, so you have two groups, N and E, which appear as the middle terms in this three-step extension, and you have a group homomorphism from N to E, and then basically using these two conditions, you see that the kernel of partial is, well, it's an abelian group to begin with, and it's, so it sits in the center of N, I guess that's, and partial of N is a normal subgroup in E that follows from equivariance, and therefore you can take the quotient. So right, and conversely, if you have a three-step extension of groups, you almost have a cross module. You need a bit additional structure, namely this map from E to N. But the way to think about it morally is that cross modules are three-step extensions of groups. Okay. No, A is really abelian. Okay, well, that shouldn't be too hard. It should be obvious. So I think the kernel tells you that basically, let's see, if you are, then this is T, and therefore you get that. All right, so that's what you get. So as I said, so the main way to think about it is three-step extensions of groups. So of groups, you can forget about this other stuff if you want to. Right. I think that's all of the categorical nonsense that I need in the sequel. At least that's all that I want to tell you. And now, so the task or the aim of my talk is to explain you how to categorify Clifford algebras. And well, to begin with, we shall take a look at just ordinary Clifford algebras, and we will take a look at them in a slightly maybe unusual way. I will give you more details and more precision maybe than you would typically need to work with Clifford algebras. It turns out that when one wants to categorify this notion, one really has to think very carefully about even some very simple constructions. One has to be very careful about identifying things. So typically, if you and if you see things which are isomorphic, typically you would tend to say, well, then we can just view them as being the same. But in the context of higher category, one has to be very careful not to do so. So one has to be very careful not to identify things which are just isomorphic. So in a sense, it will be important to very carefully go through this simple linear algebra stuff, Clifford algebras, which you all know. So let's start from the beginning. What is the Clifford algebra? CLN. Well, it's the algebra with n generators, E1 up to En, and these relations. So if you like, so here at the moment I'm working with the real numbers. We will switch to complex numbers in a few slides. But yeah, if you like, you can add a Z2 grading. This comes naturally with basically putting all the generators into odd degree. And it's also a C-star algebra, so if you like, you can do it as a C-star algebra, but well, if you don't. It's a real C-star algebra. That's right. Well, whatever you like. Okay. Well, I mean, it's easy. I mean, it's well known how you, classify these algebras. Basically. These are isomorphisms. That's right. That's right. I shouldn't identify. Actually, that's we will come back to that. It will be important not to identify. But okay, so you can continue this, and it's all well known. You get this eightfold periodicity, and so on and so forth. So what will be important for us is a brief review, or one important reason why Clifford algebras appear in geometry is that they're related to spin groups, and they give a nice way to realize the spin groups. So let me briefly review how this comes about. So inside the Clifford algebra, you have the subspace spanned by the generators, and this is just Rn. And now one can look at the subgroup of the invertible elements in the algebra CLN, which are just of the form, well, take k unit vectors in Rn, so we take Rn with the usual Euclidean norm, and take a product of those, even number of those, and well, look at the subgroup in the invertibles. You get this way. And well, actually, it's unitaries. These are the unitaries. But okay, so this is how you get the spin group. And well, so the covering map to SON is also given quite explicitly. Spin n, since it's a subgroup of the invertibles of CLN, it acts by conjugation on the algebra itself, and it turns out that it preserves this subspace Rn consisting of the generators. So, and it's isometric on that, and in this way you get actually these homomorphisms from spin n to SON. And basic fact is that this gives you realizes the universal central extension of SON for n at least 3. So, okay. Right. So good. So far, so good. So that's the spin groups. And right now, to simplify, we will move to complex Clifford algebras, and probably everybody feels more comfortable with complex algebras anyway. Let me just point out that in this categorification business, it's actually a subtle thing to treat the real case, because basically one first has to understand the complex version, and then to go to the reals, one basically has to take, going from a complex algebra to a real algebra basically means to take into account an involution, so an automorphism which squares to 1. And in the categorified setting, well, you also will have such an involution, but you have to be careful to take, you cannot just take the invariance, you have to be more careful. So it will simplify things a lot by working in the complex set. So that's what we will do. Anyway, so just take your algebra CLN, cancel it with C, you get the complex Clifford algebra, and well, you can also define it directly, of course. Just instead of looking at the real algebra with generators and relations, you just take the complex algebra. It simplifies things in the sense that the structure of the algebras gets easier. You just have basically matrix algebras or direct sum of two matrix blocks, depending on whether dimension is even or odd. All right, so very, very easy. It's just we're talking about finite matrices. It cannot be simpler than, cannot get any simpler than that. Right, one more review of, well, further structure here, spinors. Let's also have a brief look at that. So let's restrict to the even dimensional case, basically for simplicity. Basically, for the rest of my talk, I will only look at even dimensions. And well, let's look at the corresponding Clifford algebra. And according to the previous slide, well, it's just a full matrix block. So there is precisely one irreducible representation up to equivalence. It's just C to the 2k, 2 to the k. So that's again completely trivial. But this is the point. Actually, one has to be. Usually you would just say, well, that's it. So let's just work with this module. But notice that this identification of S with C to the 2 to the k hinges on identifying the Clifford algebra with matrices, and this is not canonical. So there is no canonical way to identify the Clifford algebra with matrices. So let's be a bit careful about this construction. So I mean, if you want to proceed geometrically, you could construct the spinor module as follows. You could basically view your vector space R to the n as a purely odd superspace, and well, it will then be a symplectic superspace. So since it's an odd degree, the symmetric bilinear form is a symplectic form. And well, you can ask, well, how can we quantize this? So well, pick a Lagrangian subspace in the complexification, which is just a maximally isotropic subspace for C to the n with the usual bilinear form. Or if you want to phrase it differently, you can pick well, a complex subspace L, which decomposes the complexification in a direct sum of L with its complex conjugate. So notice that V complexified is a complex vector space, so we have a canonical notion of complex conjugation, and well, this is an equivalent way of phrasing what it means to be Lagrangian. So it's important here. This direct sum is now orthogonal with respect to the Hilbert space structure. Anyway, so once you do that, you can just take as your spinor module the exterior algebra of L, and well, on that the elements of VC act as creation and annihilation operators as usual, and using that, well, you can write down a couple of identifications. So the Clifford algebra, well, as a vector space, it's just the exterior algebra of VC. And using this decomposition, you can write it also as the exterior algebra of L, tensor exterior algebra of L bar. Or if you like, S tensor S bar, which in turn is basically the same as endomorphisms of S by, I mean, this is just another way of writing matrices. Take your representation and take S dual. So S bar is also S dual canonically. So that's all. There is nothing natural here. I'm only claiming that it's a naturally CLN module here. So these are, I mean, this is just a vector space. No, I don't. No, I mean, this is basically okay. This is the. I mean, I think it's still a natural map. So you basically do the. This is the symbol map. So this is the symbol map, if you like, and So anyway, the reason I mentioned this is because you can see here a splitting of the Clifford algebra into, well, basically a holomorphic part and an anti-holomorphic part, so S bar. And this is something which appears in conformal field theory as well, and it will be very important that basically this decomposition is what in conformal field theory corresponds to the holomorphic and anti-holomorphic parts, or the chiral and the anti-chiral part of the full conformal field theory. So there is some trace of this structure already in this finite dimensional linear algebra setting. Okay, so yeah, this is a very complicated way of looking at n by n matrices and c to the n, but I will even throw more things at you to look at that. So let's fix a polarization, a very specific one. Let's start by identifying our real vector space V, which is just R to the 2k, with C to the k. So we can do that certainly. So basically fixing a complex structure. And well, once you fix such an isomorphism, you get a polarization from that. Just if you complexify, you can take the plus minus I eigenspaces of the complex structure. Yeah, and these define your polarization. And so later on, we will do something similar. We will start with a very specific polarization, and then I will argue that to get all other meaningful polarizations, we will have to act on that one with a certain group. And here, well, to obtain other polarizations, one should just start from this one, and one can act with, well, elements from SON or SO2K, if you like. And just to spell that out, I mean, there's nothing really going on here. It's just basically I act with the action of SON on my Clifford algebra. So let me look at the unitaries which well, come from the real part of the Clifford algebra, basically. And in this way, I get basically group isomorphic to O2K. And using these unitaries, I get, starting from my polarization I fixed in the beginning, I get all other interesting polarizations by just translating them with these unitaries. Okay, there is one little twist here. So, I mean, in principle, this condition up there just specifies orthogonal transformations, and I want to restrict to special orthogonal ones here. So, if you like, picking a complex structure on R to the 2n, it also fixes an orientation. In a sense, I don't want to destroy the orientation that I have on this space. But okay, so this is how I can define spinors. Okay, more remarks. If you fix an orthonormal basis of your polarized space L, then you also get a nice orthonormal basis of well, basis of the Clifford algebra. Well, just basically taking wedges of the basis vectors, and similarly so for S and S bar. And using this, you can write the multiplication in a very simple way. And well, this all follows immediately from by construction, basically. Okay. Now, okay, maybe I'll go through the next few slides a bit more quickly. So, just as a warm-up to get used to two groups, one can actually view the spin group as a two-group. So, it's not that one learns anything substantial from that, but it's instructive to do so. So, before I told you that two groups are basically three-step extensions of groups. So, you can just force the extension that we looked at, which is a two-step extension. You can just make it a three-step extension by adding 1 at the end. And in this way, you get a two-group, right? And similarly, you get an extension by looking at, well, the Clifford algebra and unitaries in the Clifford algebra. So here, this is the unitary group of the Clifford algebra. And, well, unitaries act as automorphisms just by conjugation, and the kernel is U1. So you get another extension, which you can view as a two-group if you want. Okay. Now, what we've done previously is basically, well, there is a canonical map from spin n into the unitaries by definition of spin n, and you get this commutative diagram of short exact sequences, or if you want, a morphism of two groups. And I mean, using this point of view, one basically can eliminate all choices that were involved in the construction of the spinor module. So basically, if you adopt this point of view, you can get rid of choices. So since this, I mean, I'll maybe just skip over this slide. So here's the way how to do that. Basically, yeah, one would look at the category of all possible modules over CLN, and this becomes naturally a representation of the automorphism of the two group associated to the Clifford algebra. But okay, let's perhaps just skip this and yeah. So what you get just by rewriting things is you get a morphism of two groups this way, and this captures basically everything one can say about the situation. Okay, so let's try to get to the real stuff, which is the categorification business. And I mean, I will tell you quite a few details in a few minutes, but I mean, the main message, in a sense, is, or the main question one might ask is, where does this higher categorical structure come from? And the source for that is actually very, very simple and well known, in a sense, although people haven't really looked at it from the point of view of higher categories so far. So the point is, basically what one has to do is one has to transport this construction of Clifford algebras and spinors to infinite dimensions. Okay, so instead of looking at finite dimensional inner product spaces, one has to move to infinite dimensions. And more precisely, we will be interested in the situation where this finite dimensional real vector space V is replaced by the Hilbert space of L2 functions from S1 into V. So, well, now, I mean, obvious thing to do is, well, you can look at the Clifford algebra in this situation, which is nothing but the Car algebra. And, well, this is, of course, a well understood object. You can also view it as the limit of the finite dimensional Clifford algebras for n going to infinity. And, well, I mean, there is no categorification here. So this is just another algebra, and, well, you could put a plus sign, but it's a graded commutator, so yeah. Okay, so there is no categorification whatsoever here. But the main difference between infinite dimensions and to the finite dimensional case is that now actually there are a lot of inequivalent representations of the Car algebra. So it's not type 1, so you have a lot of inequivalent irreducible representations. And this is actually why you get an additional layer of categorical structure. So this is, if you like, this is the main observation that one should make at this point. And to actually unravel this and to explain this, unfortunately one has to put in quite a bit of machinery which comes from conformal field theory and the theory of vertex algebras. So yeah, this is what I will try to indicate a bit, but I mean, in a sense, the main message is that the reason why you get an additional layer of categorical structure is precisely the fact that you have inequivalent representations, a large number of inequivalent representations of the car algebra. Okay, very briefly, conformal field theory. So there are various mathematical frameworks for describing conformal field theory, and one of them is vertex algebras. And I will not say very much about conformal field theory at all. Just very basically, one always has to distinguish between chiral CFTs and full CFTs. And basically, mathematicians, for the most part, concentrate on chiral CFTs. So when mathematicians speak about CFT, they usually mean chiral CFTs. For the purpose here, we will have to deal with full CFTs. So, right, and basically, yeah. So that's the structure you find in this context, the mathematical structure. Okay. Well, I guess. So next question is, what is a vertex algebra? And I have included the definition here, but I'll just be very quick. So if you have seen this before, it's basically, this is almost the definition of a vertex algebra. It adds a bit further structure, namely we want a unitary structure on our vertex algebras. So so we want the state space to be a Hilbert space, or at least a dense subspace, to have a nice Hilbert space completion, and the structure to be compatible with this Hilbert space structure. So in a sense, if you like, vertex algebras are generalizations of commutative algebras, and we are looking here at the vertex algebraic version of commutative C-star algebras. So it's like passing from algebras to C-star algebras is like passing from vertex algebras to unitary vertex algebras. Okay, here is the axioms, and I will just, I mean, as I said, so, well, more axioms. So the first ones are just usual vertex algebra axioms. The important additional one is the last one, which explains you the unitary structure of your vertex algebra. Yeah. So, well, yep. Yep.
What's the relation exactly to the Virasoro algebra?
Yeah. So the Virasoro algebra. Oh yeah. So you will get, so using this Virasoro vector, you get a representation of the Virasoro algebra on your underlying state space of the vertex algebra. So this comes automatically with the representation of the Virasoro algebra. Yeah, I mean, in the simplest cases, you could just basically take the Virasoro algebra and representations of that to create vertex algebras, but there's more. So you also get affine algebras and the monster vertex algebra, things like that, so it gets much more. Anyway, so the reason to include more structure is that it allows you to do more things that you cannot do with just pure vertex algebras. So basically, instead of working with formal distributions, as one would do in vertex algebra theory, one can work with actual distributions in this unitary vertex algebra framework. And this is important to get, to get a representation of the string group later on. So anyway, let me briefly tell you, there is just one vertex algebra we will need, basically, and this is the free Fermion vertex algebra. And okay, I will probably be a bit brief by going through this. So essentially, what we're doing is we are looking at this Hilbert space of L2 functions on S1 with values in our finite dimensional vector space, and we make it into a vertex algebra. And there is a well-known way to do so. And well, so one first works algebraically. So instead of L2 functions, one takes polynomials, and there's a little twist. One has to work with, not with the functions on the circle, but on its double cover. But okay, so basically what you get is, well, this decomposition of your state space into periodic and antiperiodic functions. And starting from that, one can build a vertex algebra. So one has to choose a polarization, and the way to do that here is basically pick positive and negative Fourier modes, and then you can form the exterior algebra of that, and this gives you the so-called Neveu-Schwarz Fock space. And similarly, if you do the same thing for periodic functions, you get the so-called Ramon Fock space, where there's the similar construction. And from this, one gets a vertex algebra. So the Neveu-Schwarz Fock space basically defines a vertex algebra. And the structure is determined by just one single vertex operator. You just have to define what the state field correspondence does to this very simple vector. And here on the right-hand side, you have the field coefficients, which are basically creation and annihilation operators on the Fock space. So it's simple. And starting from that, one gets the full vertex algebra structure in a unique way. And the physicist would just write down these fields, and they would say that they satisfy these operator product expansion. Okay. Now comes perhaps first important new step, which consists in actually recalling what we did when we constructed the spinors in finite dimension. So remember that when picking the standard polarization, I said, well, we should identify r to the 2k with c to the k. Okay? And in a sense, we have to do something similar here, but on a categorified level. So in other words, instead of working with real fermions, we have to pair two real fermions into a complex fermion. You can do that. You get another vertex algebra in this way. And this is like passing from from R2 to C, and that's what you get. Now, okay, I'm running a bit slow out of time soon, so let's see. Let's have a look at this complex fermion vertex algebra, and let's begin in the simplest situation, namely where this has rank 1. So just basically looking at just C and not C to the K. And this vertex algebra is very simple. It has just one irreducible module, so it's a rational vertex algebra, which means that there are only finitely many irreducible modules anyway, but there is just one irreducible module and also just one twisted irreducible modules. And you get these fusion rules for these modules. So that's as simple as it can get, basically. And now we need one further ingredient. We have to fix a full flag of C to the K. Now to move from one complex fermion to K complex fermions, if we fix such a full flag, we obtain corresponding isomorphism of the vertex algebra C to the K as a tensor product of just rank 1 complex fermion vertex algebras. And we get a couple of modules which are just obtained by taking the modules we have in the rank 1 situation and tensoring them. Now, these modules are basically the replacement of the basis vectors in the Clifford algebra in finite dimensional situation. So, instead of just a vector space, we now get a category of modules. So that's perhaps the important step here. Doesn't really matter too much to understand this vertex algebra formalism, but the point is basis vectors in the finite dimensional situation get replaced by modules. Yeah, so that's what you get. And then you can define your categorified Clifford algebra, at least the special part of that. Well, you just take those modules and you get a category. So that's already a good thing to begin with. So instead of a vector space, we now have a category. And well, this category is also not hard to describe. You can exactly say how the simple modules look like. They will all be of this form, which basically is like, well, the same parameterization as for the basis of Clifford algebra in finite dimensions. Okay, now once you've got that, you can define a multiplication which mimics matrix multiplication. And well, this doesn't come out of nowhere. This is actually something which also appears in conformal field theory. I'll not go into this, but there is a good reason to look at this multiplication. And it reproduces. Oh, this check is the dual object. So you take, this is a category with duals. So anyway, so this way you get your category with multiplication, and you can also write down a modular category over that, basically by just repeating the same construction just with one chiral copy of your complex Fermion vertex algebra. And well, this way you get a modular category, and it really corresponds to the spinor module for finite dimensional Clifford algebras. Now I will finish by basically telling you what makes things more complicated in this whole situation. So basically, so far we have just constructed a category which looks like some direct sum of just vector spaces, basically. It's not a very difficult category. But the point is that what we have done previously, we have made various choices in the construction. And I said in the beginning, one shouldn't do that. One shouldn't make choices, or one at least should keep track of choices. And so what are these choices? Well, we had fixed the polarization to begin with. That's basically like in the finite dimensional situation. That's something one should get rid of here. We fixed the flag, and we also fixed, that's perhaps something which one doesn't even notice at first, is we have fixed the parameterization of the unit circle. Basically picking this parameter z, this coordinate z, means that we fix the parameterization of the circle, and one shouldn't do that. So physicists tell you that this is nothing, one should make things independent of parameterizations. Okay, and yeah, now basically the real work is to understand what happens if you get rid of all these choices, and you get a much larger category. So basically you have to take into account all these choices, and you get a much larger category, which then gives you the right notion of the categorified Clifford algebra. So just maybe give me 1 minute to wrap up, so I'll skip through the details of how to do that. Let me just indicate why this construction, is probably a natural one. It is closely related to the string group. So the string group, what is the string group? It's the correct replacement of the spin group in finite dimensions. And technically it's obtained by going one step further in the Whitehead tower of ON. So you kill the first 3 homotopy groups of ON, and then you arrive at this group string n. And well, people have looked at that a lot. And it is most naturally viewed as a 2 group and not as a group, it turns out. And there is a very nice model for this, which was developed by these guys. And going back to what I told you in the beginning, basically 2 groups are 3-step extensions, and here there is a very nice 3-step extension which involves the loop group of spin n. So yeah, you have U1, then the universal center extension of the base loop group of spin n, that maps into the path group of spin n, so just smooth paths in the group spin n, starting at the identity and ending somewhere, and then you can evaluate at the end, and you get back to spin n. And this gives you a 2 group. And well, if one unravels all the constructions, that all this coordinate independence and everything that I haven't told you, then what one gets is that actually this categorified spinor module gives you a representation of the string 2 group, or a 2 representation. And this is something which was basically missing in the literature so far. So we can give various models of the string group, but it wasn't quite clear how to find geometrically interesting representations, and I think that this is a first step in this direction. So thanks very much. Sorry, what? Yeah, I do have. I mean, basically, you would have to do a similar analysis for bosons instead of fermions first, which is more complicated because the vertex algebra of free bosons is no longer rational. But yeah, I mean, one can at least speculate about what this such a guy might look like. But I mean, this is still, still a lot of things to be understood. Oh, the index would give you the written index, basically. So, right, so.
You mentioned that categorification are not unique. Are there any other possibilities that are not, well, which might be interesting, or is it so far the economical?
No, I mean, it remains to be seen whether this is really a useful way to look at the problem. And I should also mention there are other ideas how to attack the problem. So there's work of Bartels, Douglas, and Enriquez. They work in a slightly different setup. And so it remains to be seen whether this is really the right framework. And I should point out there is a good test question one would have to understand. Namely, in finite-dimensional Clifford algebra theory, you have this periodicity phenomenon, right? So in the real case, the periodicity is 8. In the complex case, the periodicity is 2. The topologists tell us that in this setting, the real periodicity should be 576. So if you can come up with an argument which shows you that this construction is periodic with period 576, that would be a justification of doing this, but I don't know. This is 24 squared. I don't know. Yeah. I mean, I think this is something at some point one has to look into this, but I don't know. No, because I mean, if you just take the corresponding modular tensor category, you lose the fact that it comes from representations of, well, or comes from free fermions, and you do no longer have this geometric picture of changing polarizations, and basically just working with a category would not, so you cannot define a representation of the string group just in categorical terms. So you have to use one or another concrete model for the corresponding field theory. So you could choose nets of phenomenal algebras, that's fine, but it's not enough just to work purely categorically. So